S test and win. Win will be sign rank Wilcox and rate. W test. The syntax of the command you could find with help. There's help on both Minitab and R. So things left out. I didn't go to the whole details. I should have mixed them. I thought I did, and I guess I got them separate items. But here's the one sample work from the ones that we use. There's not a sign test, but you can download this one if you want to. It's one I put together. You just click here. Okay, go there. The one we haven't talked about here is moves test. We'll talk about that in the next couple of minutes. So I put some R functions. Yeah, this is all the R functions. I'll try to update this too. There's the sample sign. Here's a man Whitney if you want to use it. Does get the standardized testing. Now you have to be careful because I think R uses the exact distribution for small samples, so that I'm not sure from the answers I've gotten. But the ones I put together all use the S. Okay, any questions on that? And we also have another page. We have RGLM we could use. So we use that from time to time. It's just drop and click. Okay. You can use it if you want to. I'll pass that in assignment. This is RGLM. It's just visual. But I think you can get it from our page too. Check it out. Here's our page. Yeah, it is. To have more, a couple years ago I lost a turf bed. I decided I was too old to fight. So anyways, you keep fighting. You got this much. You can do a few things with it. Here's one example. Pick on one sample. Here's an example. You just put the data in. And you can browse. And then there's all kind of options. You just want to do the Simon full clocks. Oh, let's do box plot too. And we're going to test 0 next time. The null value is 22. That makes sense with this data. We'll find out. And then it comes back with the results. So here's the Hodges limit estimate we're talking about. Here's the standard error. And that would be the T ratio testing 22. For quite a while, I was talking about side-by-side analyses. But that's what we have here. We have, this will be the non-parametric, and then this will be the traditional t-test. here's the sign rank test statistic. Z test is 0. It could be. Oh, this is missed. That's not good. The confidence interval is. That seems to be the one. But there's a lot. Something's wrong with that test. So I'll give you an assignment today, and then you can use whatever you want. You can use Minitab. Or if you want, you can use some of this problem. Sure. Probably best to use either Minitab, because then you get your data in, right? You can save your worksheets in Minitab and your data files. Or you can do the same thing, right? At least on Windows, it's easy, right? Because my daughter works with Windows. Right? My one goal is to try to stay away from Windows as much as possible. Most of my employees are saying, I don't have that. Let's look at this big problem, big yeah, it's either 10, 31 or 32. Okay, so suppose we have, should be able to make this good. So we have these big samples, 12, 26, 29, 25, and y is equal to 9. So let's work through the man Whitney on this. And if you have any questions, please ask. So we're going to do this one by hand. We don't need to do it for this one. So let me just copy the data. So x is 12, 26, 29, 25. And y is 23. Okay, and that's a two-sample problem, just test mean of x. Okay. Okay.
Isn't that up there?
Okay. So let's test, and I don't know, let's just test, I guess, greater than 0, right? Or the difference, right? It's, so let's test theta y. This is what we've been calling delta. Minus theta x. Okay, we know our test statistic is it's W, but someone knows that. Okay. So for this, I should, this 25, just park it here. It really helps if you have everything pre-sorted and do it by hand, right? And then you just combine the data. So this will get rank 1, 6, 2, 3, oops, 1, 2, this gets 4, and 5, 6, 7. So then W would be 17, 24, 29, 30, right? And in this case, N1 is 4, and N2 is 5, N would be 9, and we expect W to be N2, which is 5, right? Times 9 plus 1, 2, 20. So we're on the upside. Let's get the p-value, p-value is a one-sided test, so it's just the probability W is greater than or equal to the observed value, which is 30. Right? Then probably should use a continuity fraction. Then you just have to standardize. We have the mean there, right? So we're 4.5 up for the mean. And downstairs we have that mess. Okay, then we could do, I'll just use this as a calculator. Okay, so my Z would be like 4.5 divided by the square root of. So it's 1.10, right? And you know you're not going to reject, you could find that value. You could either use the table or use the calculator, whatever comes out to, what, 13%. Any questions on that? That's all straightforward, very straightforward calculation. Just combine the data and rank them. The sum of the ranks to lines. Just be careful. I haven't been saying this in this class, but if you line things up correctly, these inequalities agree, except this one is really strict. One side the other way, then it would be W too small. And if it's two-sided, well, if it's two-sided, if you're doing it by hand, the best thing to do is just decide whether you're on the upside or the downside. It's just shifted up from the axis. think I've used this notation. Script L stands for the law, but it means distribution. So I can model it like that. So the algo's just shifted up. It's the shift, right? Always try to, make sure you know what you're computing. Avoid a dumb error. It's just the difference in means or medians. And it's just the median of these differences. And that's not too bad in this problem, all right? We could put down a table of the differences. Certainly in a big problem, you don't want to do that. You have n1 times n2 differences. So if you have sample sizes of 30, well, I'd like moderate sample sizes, right? And that's 900 differences. You're not going to do a table. In this case, I mean, it's not a big deal. You want to do y minus x, it's easier for me to put the y's on top. And make sure you put the data in order. It really helps when you start looking for things. So here's my x's and my y's. And now I'll just make a table of differences. So if I haven't made any mistakes, which is probably fairly likely, we have like 20 differences. Now you can put those in order, but there's a partial order in the table, just use it. Okay? So we're after the median of the differences. So there are n1 times n2 differences. So the median would be the average of the 10th order difference, right? So let me just go through in order to get to 10. This is 4, 5, 6, 7, 8, 9, 10.
You get 2 6s.
So this would be 10. So it would be 6. Yeah, you have to watch. Now you need the cutoff value. It's in the book, right? Cutoff value is it's the mean. And then that's the difference. And then you just round to the nearest number. And then you just pick the C plus 1. Right? negative n1 times n2 minus. So again, with this small data set, that's not bad. So C is what? 10 minus half, and we'll do 95%. If I get it right, it comes out to 1.9, 1.5. I guess you could round it to. Okay, we could have done that. D is 3. D 17. This would be what? 1, 2, 3. Be minus 14. And that would just count that. 2. So it includes 0, and it's not surprising. We did reject.
Should be 18, right?
What?
20 minus 3 is 2. 18.
Oh, it's 18.
And then, do we want the 90% interval?
Oh, is that what I asked for?
Yeah.
I'm sorry, then you get 1.645. I get the same answer. Well, I wouldn't with 90%. What did C come out to?
2.78.
So you round it to what, 3, 40? So it would be, it's shorter, it's more precise. You've gained precision, but you've lost confidence. Now you can show algebraically, really, it's kind of maybe you might want to try it. You can show this. Right in terms of delta, if you're doing a two-sided test, you can move with the confidence. You can reject H9 and level out. But 0 is not in. 1 minus alpha times 100% confidence. This test is equivalent to the manual. Sometimes run into people that think they know statistics, and then they think confidence intervals and tests like distinct items that they know. At least in the simple ones, you can always do one. You can do it by confidence interval, or you can do it by the test statistic. You'll get the same result. Now, the confidence interval doesn't give you a p-value. You can stretch the interval till it hits 0. I've never done that. I mean, you do run into people that think you should have been confident. And I've run into people who think that you should only do tests. Okay, see, I don't know the p-value. So here's 0, here's my confidence interval. I reject H0. What's the p-value? I can't get that. Maybe this is like 90% or something confidence. Yeah. But if I stretch that till it hits 0, then this will be changing. So maybe it hits 0 at 99%. The p-value is oh, okay, then tau hat. If you had two samples, you could actually get 2 tau hats using the sign rank Wilcoxon, but in the 2 sample problem, you don't have to assume any sample. That's the neat thing about one of the neat things about these rank tests when you get to 2 samples. And that would be true in all the models we talked about from this point on. Well, I take that back. This one we'll talk a little bit about. But I don't have to assume symmetry. So I don't even want to bring in this on the forecasting. This test in a file that gives a book doesn't depend on symmetry at all. It's just the length of confidence. It's just standardized slightly different. And the standard error delta hat is this tau hat times this array. So you could do that. Let's do the 95% one. Length is 34, right? So this. So it's 12.93. Standard error of the hat would be 12.9 times this. So it would be about 8.67. About 8.67. So then you would use delta hat. times 8.7. 16, looks like it's a little bit, it's about the same length. Actually, it's not down. So that's proportional. Hopefully I made all the calculations correct. This different. The length is about the same. Any questions on that? Any questions on the math with you then? Let's do moves first. Okay, so we talked about the one sample problem, we had the sign test and the sign rank Wilcoxon. So we got two sample problems. And we talked about Man Whitney Wilcoxon, which is an analog of this sign rank Wilcoxon. And then an analog for the sign test. Oddly enough, the analog is more complicated. Talk about it later for estimation. But for today, let's just talk about the test because the test is used quite a bit. The estimates we're talking about. But we'll definitely talk about the test. This is often called Moods Median Test. And it's so simple, it does come up quite a bit. And, references, so it might not be you can find them any. Good example of solving. Now it's a sign, so you're counting things, and we pick on the y's. Reverse y next, you'll get the same answer, the same p-value. And we just we get the combined sample median, and then the test is simply to count the number of y's which exceed that y. Okay. It's called big M magic, the median of all the x's and y's. You don't worry about counting them if they're equal to m hat because you've thrown them all out, okay? All those x's and y's are gone. So you don't have to worry about it. It's either greater than, and that's a test statistic itself, and you can show it has a hypergeometric distribution. But if you know something about statistics, that keys you in right away because you need to do a features exact test, which is in a chi-squared table. But in this class, we'll probably just use, I think we'll just use the usual goodness fit chi-squared tables. Because we talked about this one, we'll just. So to do that, here's the table, it's a 2x2 table. Okay, and the x is here and the y is here, and then these are the number below them, and these are the number above them. And then actually your m sub 0 plus is this square. Remember in a chi-squared analysis, the degrees of freedom are the rows minus 1 times the columns minus 1. Right? There's only one degree of freedom. There's only one free cell. As soon as I stick in that, the rest of the table is known because the number of y's, the number of x's is n1, right? Now it might be like n1 star because we've thrown out the ones that n hat. But for the moment, let's just do it that way. And I know those values. So if you give me this, then I know every other thing in the square. Well, actually, see, and this is actually all the margins of this thing. Because this has to be another 2. Now, even an odd comes into play, so you don't worry about it really, you just set the table up. The computer's going to do the margins. But let's assume that none of the values are equal to n hat. So this indeed will be n1 and 2. Okay. It's got to be, this is a combined sample size. So as soon as I stick in at m0 plus, we're done. Now I can do all the computation. And the test statistic is chi-squared is just the sum of the rows minus the e's squared over the e's. And then the e's are row total times column total over the total number. Okay. So what are you comparing? What's the deviation like in this cell? So E22 will be N2, right? Times N over 2. Divided by N. So it would be N2 over 2. That's right. If H0 is true, then you expect half the y's to be above the mean. So the expectation is exactly what it should be. And then, but of course, you're going to just let the machine get everything. Do with these meetings. Okay, so if we go through this, there's 9 items. the combined median would be, the fifth ordered item, which actually is 28. There's 5 x and y is less than 28. So in our example, n hat is 28. And then the number of y's above it would be 1, 2, 3. Now you would throw out this one, right?
What, the 29?
Let's see, so okay, so there's 1, 2, 3, y is above. How many x's are there? Just a 29. Right?
Yeah.
How many y's are below? Well, did you throw out that 28? So there's only 1. How many x's are below? There's 3. So that's 4 and 4. We threw out 1. It's 1. You're comparing 3 with 16 over 8 over 2. I don't think we're going to get which one. Any questions on how I got it? Just a simple counting thing. It's a chi-square test. Now, how about we have troubles with p-values, except if you're doing a two-sided test, immediates, right? Chi-square is statistic, and we just rejected it's too large. And P will be this will be the observed chi-square. So what if it's one side? If it's one side, you've got to make sure you're on the right side, and then you just cut the p-value by 2. You have to be careful. You can get it from the sign of m naught plus the when you figure out m naught plus, you know it's above 2. It's like you maybe have to keep track of this. So if I was doing a one-sided test where delta was greater than 0, okay, I'm okay, and my p-value will be half of what I calculated. If, on the other hand, I was testing delta less than 0, and I came out with the same value, then if you're smart, you just stop because the p-value is over 50%. But, we're actually looking at we want the probability less than. So you still cut that too. You wouldn't have it. And we need to have so we just put this table in. Just like it appears, table 1. command is this, you could click for chi-squared. If you do a command, which is C1 dash C2. I didn't bring the mini tables. We could do it more. I just have to put the date. With those rows, easier if you just put in a matrix or a table. Okay, and I can just do CHIS, and I think it's CHISQ dot test. The p-value is 0.4795. It's small samples. You can act sophisticated and do Fisher's test. Fisher's test. Oh, I don't know its command. No, p-value is 0.0. In class, we'll just do the chi-squared test. Okay? Just pick on that one. Yeah, usually about this. Now there's a confidence interval. We could actually we'll probably won't discuss the confidence interval for based on the point estimate. It's just a difference. I think this is the Hodges Lehman one we're talking about. Switch. Again, it has very low efficiency. I don't really like it. If I'm consulting with someone, they want to do a news meeting. Okay, now, so I think now we can do the sum. So let me pass it out. I got 6 data sets. It's doing your own work. So I can put your name on it. Hi, Lauren. Someone Cassidy is not here. Okay, sign rank Wilcoxon, sign. We talked about those in Tavenor, t-test. In R, it's T dot test, right? So that's on the first one. If you're an handicap person, you do W test, right? That's test, that you can do sign test. And T test. With an R person, you do zero top stuff. And then for the sign, you can use that function for the talk. Download that if you want to. Yeah, this one's interesting. Now, if you look at that, it's an R function, and you can ignore all this as long as you set things up correctly. You want alt equal to 0, run it twice. That's the one nice thing about computers, right? I don't want to worry about the alt, so I'll just subtract the null value off of my x's, and I'll run that sign test. That'll give you the right test. It'll give you the wrong confidence interval. So then you can run it again with just x. And the first time, that's the command the first time, and the second time for the confidence interval or whatever, just type in that. So we'll have to download the source of it. It's scary if you look at it. You don't code. My programs are easy to read. One guy I worked with in college says, listen, my R program is free. So that's right.
Also have quizzes for us from a week ago.
Yeah, no, but to be on, not to be on the back end. So. Oh, sample size estimation, we should go over that, better go over that. We did sample size determination for PHAT, but we can also do it for these location problems. And again, the easiest one is to base it on the confidence. Okay? So again, what people have to say, okay, I want to estimate theta. Let's say we're doing sign like 4 o'clock. I want to estimate theta within B. With confidence 1 minus alpha. Okay, well then, what's the error? Do the symmetric confidence interval, and that's one to pick on. It's just this, right? So this is what you want less than or equal to B. And then if you solve for n, that, right? And it's the square. Now to use this, you know alpha, so this is done. And you know B. And The only unknown usually is that tau. But in this problem, you have a pilot study, okay, you have a data set, just use that. Just use the value tau from that. There's no conservative approach. You don't have P times Q less than or equal to 1/2. P times. Okay. So in this case, you really do need a guess. Once you have it, it's you can determine it. Need. In fact, if you're doing consulting, then and the person who claims his data is going to be fairly good, you might just put in sigma hat. You might know, you might have a good guess at sigma, and you're not going to do that for a while. If I jump a bit, if you think there are going to be outliers. Let me just go that one. Then 5 is test what you're talking about. Right? And 2 tests you want to do, so I know what I want to get into about. We can talk about R for the 2 samples. C1, C2, where the columns are, and you should be thinking that C1 dominates C2 and all the output. I mean, your estimate will be based on that. C1 is like the Y's, and C2 are the X's, the flags. You can do moves by hand, just get it, lose a count and get it in the table. It used to be 2s, I was going to check that. Let's do the 14. That I'm not sure of it. I don't use many tabs that much. In the back of my mind, I think that command has changed. Does anyone know? How about R? It's the same command. You just put the, and I think again it's the first one over the second. And then you probably want confidence intervals, so you'll have to add this statement. The testing confidence interval is not a problem with the 2-sided test, as long as you're testing 0, which you usually are in 2 sample problem. And then the t-test is this. If you want the quantity, you have to do this. You do y x. I think it gives you the confidence interval anyway. And then it's var dot equals true. Otherwise, if you don't do that, you'll get Welch's test. Shouldn't matter. Now, how about if I ask you for moves? I put a function in. Didn't calculate it, okay? It just gives you the matrix. Net move. It comes back with the matrix. And then gosh, from top. So you would run it this way. Or you can just put functions together. The bad news about the command, I mean, the turnout isn't very good. If you ask for help, it'll tell you how to get the expected frequency. So print out from any tab, well, I had to check the data, it used to be really good. From a chi-squared breakdown, what you want, of course, is you want the table of counts, thing you put in, and you want the expected frequencies in the table, and it doesn't hurt to put what goes into the test statistics. Where you can always spot things, right? Often their chi-square test is like a first test. Oh yeah, of course, you're dependent. When we talk about dependence, I mean, you're testing for independence, and if you fail to reject, then you don't know what you're talking about, probably. But it's these sums that are so important for further analysis. You want to know where the big things are. Okay? Where are the big discrepancies? And it's nice that they come out. Minicat used to do this, and we always come out. And you can spot the big discrepancies. And also you can see this thing on the top here's like residual. Any questions on that one? It's sort of straightforward, right? There's no tricks in it. I think it's a good review of what we've done. Now, due date, I put Thursday on it, but I was going to pass it out on Tuesday, which I didn't. I would try to get it done before spring break. But I won't hold it to. You might have a lot of questions on Tuesday. And on Thursday, you'll have to do it. Then you can go forward.
How it's supposed to look.
You're not going to report, I'm stuck here this year.